Hi there, welcome to Superphysics, the online physics tuition service. This is question 6 of the WJEC AS Physics exam Unit 1 to summer 2016. So looking at question 6, we have a projectile question. And we have a sphere on the surface and you've got the curved path as shown. And the question asks us to describe and explain how, if at all, the vertical and horizontal components of velocity of the projectile change during the flight. And what's common with most of these questions is we can ignore the air resistance. So first of all, for our projectile, this is my projectile at each point in the journey, the horizontal velocity never changes. So if we draw on the velocity vectors, we should find that the horizontal velocity vector never changes, okay? However, the vertical velocity does change. It's going up and down again. Therefore, if we just consider the vertical direction, vertical velocity, that would have to change. So initially, it's quite a large vertical velocity. It's getting smaller here at the top. You can almost imagine like it is hanging momentarily in the air before coming down again. And this point here, there's a small vertical velocity, and this point here has a much larger vertical velocity. So in the y direction, there is acceleration. In the x direction, there is no acceleration. So describe and explain how the vertical and horizontal. So you can say for the vertical velocity components, the vertical velocity decreases to the maximum height and then increases. Okay, that's describing it. Explain it because it changes velocity because there must be some sort of acceleration. Now, to cause acceleration, there has to be a resultant force. So because gravity acts in the downwards direction. That's dealing with the vertical velocity. Now we talk about the horizontal component. So the horizontal velocity always remains constant because, so remember to explain it, because there is no force in the horizontal direction to cause any acceleration. Okay, and that's our first part of the question done. Question 6b, sorry. We got a newspaper image or clipping about the Philae landing on the comet 67P, and we're told some information here. It bounced twice before coming to a rest, and we've got the image here. Use the information in the image to calculate the horizontal velocity of the lander in the first and second bounce. So here's the first bounce, here's the second bounce, and we're told, so if we were to draw it out properly, like in the first part of the question, that is essentially does that. And this is the first bounce, that's the second, where it sort of lands the second bounce. And we're told that it travels the first bounce about 1 kilometre up and an equal distance across. So from there to there is 1 kilometre. And we're told the hang time is 1 hour 50 minutes. Okay, so because there's no acceleration in the horizontal direction, we can just use speed, distance, time equation. So velocity in the x direction is the displacement in the s direction over time. The horizontal displacement is 1 kilometre, so 1,000. And the time taken is, again, it's going to be 110 minutes. So 110, and there are 6 seconds in 1 minute, so times that by 60. Comes out to be, so 1,000 divided by 110 times 60. And that gives us an answer of 0.15 meters per second. Okay, moving on to 6b part 2. By considering the first bounce, show that the value of the acceleration due to gravity on the comet is approximately 0.0002 meters per second squared. Now, because we're dealing with vertical motion now, we're going to use the Suva equations. Okay, and if this is the flight path, okay, then we're going to talk about the second half of the journey. Okay, so let's fill in what we know. So x is the vertical displacement, u, v, a, and t. And I always write these down in the margin of the page. It helps me solve the problem. It tells the examiner what I'm trying to do. So if we consider it from here down to there, the initial vertical velocity here is 0. It's neither going up, it's neither going down. Imagine it hanging in the air. We want to work out the acceleration due to gravity, okay, which is going to be a. We're told the hang time. The hang time was 150 minutes, or 110 minutes, sorry. Because projectile motions are symmetrical, the first half is exactly the same as the second half. The only difference being the direction of the velocity, the vertical velocity. So the second half of the journey, the time is going to be half of 110 minutes. So time is going to be 65 times 60. No, sorry, 55 times 60. And that will give me the number of seconds for the second half of the journey. Okay. And we're told that it travelled a kilometre into the air. So the ix direction is 1,000 meters, and we know to use a Suva equation, which has all those variables without v. So let's look at our equations of motion, which are these four here, and we want something without v in it. And the only one without v in it is x equals ut plus half at squared. So write out the formula: x equals ut plus 1/2 at squared. Now, because we know the initial velocity is 0, that whole first term there disappears, because 0 times anything is going to be 0. We can just ignore it, and then things will be a little bit easier for ourselves. So x equals 1/2 at squared. Now we want to work out acceleration, so we've got to rearrange this equation here for acceleration. So if we got half on the right hand side, so we times it by half. If we divide by half, that's the same thing as times it by 2. And we divide that by t squared equals a. Okay, so 2 times 1,000 over, and then we work out the time, so 55 times 60 is 3,300 seconds. So 3,300 seconds squared, so 2 times 1,000 divided by 3,300 all squared gives you 0.00018 meters per second squared, which is approximately equal to 0.0002 meters per second squared. Okay, give 2 marks. Part 3 of the question. Show that the vertical velocity of the lander immediately after the second bounce, so just here, there, was greater than 60% of the escape velocity. Now, the escape velocity in the very bottom corner here is about 88 centimeters per second. Okay, so what we need to do is we need to find, this is now the first bounce, and this is the second bounce. We need to find the initial velocity there straight after the first bounce. Okay, so again, we're going to use a Suva equation because we're working vertically. So let's write out what we know: x, u, v, a, and t. Now we know the acceleration is 0.00018. Okay, we could use that number, or we could use the one they tell us. Little exam tip for you here: if it's ever part I or part II, put III. Chances are the questions are linked, so you'll need to use something in the previous question to help you in the next question. Now, because they've told us what the answer should be, that's a clue that's going to be used in the second part of the question, or the third part of the question in this case. So even if we got this completely wrong, we can still do this part because we know what the answer should be. Okay, so let's put the acceleration is 0.0002 meters per second squared. and we're told the hang time again is 55 minutes, so 3,300 seconds, and we want to work out the initial vertical velocity, and the velocity at the top here is 0, and we know it travels 1,000 meters upwards. Now we can use any of these equations of motion that we want to. Let's use V equals U plus AT. We will go rearrange it for U, so U equals V minus AT. The final velocity is 0 minus 0.0002 times by the time, which is 3,300. I should really put a minus in there because it's an acceleration due to gravity. So initial vertical velocity is 0.002 times by 3,300 comes out to be 0.66 meters per second. Now, my escape velocity in the article was 88 centimeters, so that's the same thing as saying 66 centimeters per second. And we need to prove that this number here is greater than 60% of 88. So we do 66 over 88 times by 100 gives you, 66 divided by 88 times 100 gives you 75%, which is greater than 60%. Part C of the question. By considering the following facts, discuss whether or not the mission or not was justified. So we've got some information here. We've got 5 bullet points, and we can sort of deal with these in each bullet point individually. So what I would do, just the purpose of this exercise, I would draw up 2 columns. So on the left-hand side, justified, and the right-hand side, not justified. Now here, it's always worthwhile just looking at how many marks are available, because we want to see the level of detail we need to know, put in. So the first one, the cost of it is about over a billion pounds. That seems quite expensive, so not justified. You say it's expensive. There are better uses for the money. Okay, so what's the that's an issue there. It's very expensive. Could the money be used for better uses in society? For justified reason, number 2, 2,000 people involved. So it's created jobs. 2,000 people created jobs. Not only for spacecraft, but also for the instruments as well. So all the money is filtered down to other smaller organisations which can make all the instruments. Advanced solar technology has been developed, so it's developed new technology which could have public benefit. Sort of, you've got better solar panels, and you can have more renewable energy. So develop new technologies. There's 28,000 retweets in the first hour, so there's public engagement. So there's public engagement. Okay, so people are interested in it. And also, they've found organic molecules in the comet surface. So they've developed a further understanding of comets and solar system. Okay, that's some of the justified one. Some not justified one. There's not much benefit to the general public, so there's lack of benefit to the public. Why does the average person on the street care or interested in this mission at all? So what's their end product for them? There are many more, but 3 marks. I would suggest 3 different points for that. Okay, right, let's have a look. Okay, that was question 6 completed. Any questions or comments or any further queries, please just leave them in the section below. And now we're going to move on to question 7.